started here. All right, so today what we're going to do is we're done talking about parametric equations. For now, we've learned everything we need to know about those. And for those of you going on to Calc 3, those are really useful. They'll pop up a lot whenever we're doing calculus in 3 dimensions or more. But what we're going to learn today is also something that will be very useful in the future if you go on that there's 3 called polar coordinates. And it's very good at getting things that have some kind of circular or spherical symmetry, as we'll see in a second. So ordinarily, when we draw points on the plane, we usually use an XY coordinate system or a rectangular coordinate system. So suppose, for example, I wanted to specify the point 1, 2. Well, traditionally, this 1 represents moving 1 to the right or in the X direction. And then this 2 means after you do that, we move vertical by 2. And then bam, by following those 2 directions, we've uniquely specified a point on the plane because the plane is 2-dimensional. So we need 2 pieces of information to uniquely specify what the point is. And if we were to draw some kind of grid for this, I've seen this on graph paper or something like that, then you can see why these are called rectangular coordinates, because all these little grids are actually squares, rectangles. And this is also called the Cartesian coordinate system because this was invented by Descartes way back when. So I'm sure all you guys are familiar with this. You know how to plot points in there. You also know how to draw functions and other curves in there. But what we're going to learn today is we're going to learn about polar coordinates, which is actually just another way of drawing things on the same plane. So we're still going to be drawing things in the plane. It's just going to look a bit different. So for polar coordinates, instead of X and Y, we're instead going to have 2 coordinates called R and theta. And even though it's written second, usually theta is the first one we think about. So rather than going this much to the left or right and this much up or down, what we're instead going to do is we're going to specify this angle, and that angle is the angle between where we're looking at for our point and the x-axis. So what I do is I start looking in the direction of the positive x-axis, I turn through angle theta, however much that is, and then what do I do with the second coordinate, r? If I'm starting at the origin when I'm doing the turning, then what I could do is I can go out however far r is, and that will specify my point. So for example, if I have the coordinate 1 and then pi over 4, what I do is I turn up to angle pi over 4, and then let's say this is 1, I'm going to go out that far once I've turned in that direction. So if I were to draw some kind of grid representing polar coordinates, I would have the grid representing equally spaced thetas. I'm going to go by pi's over 4 here. So I'd have all these diagonal lines converging at the origin. And then for my r, what I would do is I would have these circles. So I'd have a circle at 1. I would have a circle at 2, representing going out 2 distance, and then it would go on forever. Now, if you look at this, this actually kind of looks like a map of like either the Arctic or the Antarctic, where everything, this point is either true north or true south, and then everything else you either move to the north or to the south in any direction. And the map of this would look kind of like that. That's why it's called polar coordinates. This is what the graph would look like, or this is what a map would look like as poles. So let's practice drawing some other points here. So let's draw the point 2 and then 7 pi over 6. All right, so 7 pi over 6, that's at least past pi, but not quite 5 pi over 4. So we're going in this direction. How far out do we go? We go 1 and then 2. So 2, 7 pi over 6, that'd be the point right there. Let's see, what else do we have here? What's another point we can draw? Well, we draw the point 1 and then 5 pi over 2. The interesting thing about this point is that 5 pi over 2 is greater than 2 pi. What we do is we go around 2 pi, and then this is 1/2 pi greater. So we go another 1/2 pi, and we're looking in this direction. And then we go 1. So that would be where our point is going to be. Now you might be thinking like, okay, well, why did we bother going 5 pi over 2? Isn't this the same as 1 and then pi over 2. And you're absolutely right. It is exactly the same point. One interesting feature of polar coordinates is that you can have more than one representation, or really infinitely many representations of exactly the same point. So these two coordinates represent the same point. Whereas back in x and y coordinates, if you have two different coordinates, then they're necessarily going to represent two different points. That doesn't happen with polar coordinates. So these points are the same, and they're both right there. And then finally, let's try to draw the point -1, 3 pi over 4. All right, well, let's turn to 3 pi over 4. That's this way. But then we see this -1. What does that mean? I thought this was supposed to be distance. How could that be negative? Well, when we see this negative right here, what we do is we look in the 3 pi over 4, or whatever theta direction, and instead of going that way, we go exactly the opposite way by however much this number is. So instead of going this way by 1, I'm instead going to go backwards by 1. Kind of like how positive x values make you go one way and negative x values make you go another towards it. So -1 3 pi over 4 would actually be right here. And once again, we have an instance of there being more than one way of representing that point. If we just spun around to 7 pi over 4, then just went normal 1 or positive 1, these would be exactly the same point. So once again, we have several different ways of representing the same point. And then finally, let's look at 100 pi, or sorry, whoops, r should go first. Let's have 100 pi for theta and then 0 for r. So 100 pi, that means we spin around the circle 50 times before we do anything, but then after all that spinning, we don't go anywhere. We just go 0. That's going to be at the origin. And one more unique feature of polar coordinates is that it doesn't, if you want to draw something in the origin, all you have to do is have your r be 0, and then your theta can be any value that you want. So this, along with 0 and 2 pi or anything else, those would all just be the origin. Okay, so that's for plotting points. Now let's say we wanted to convert either points or maybe equations from either rectangular to polar or polar to rectangular. So we want some kind of way to convert these coordinate systems back and forth between each other. Because sometimes something's easier to do in one coordinate system, and other times it's easier to do in the other. So we want to be flexible, know how to change between them. So how do we get a relationship between x, y, and then r and theta? Well, we're going to draw this picture right here. Imagine these are the normal x, y axis. This is the plane. And then we have our x value for our point, our y value for our point itself. This is how far it is from the origin. And then this is the angle that we turn to face in the direction of the plane. So by using this triangle and trigonometry, what we can do is we can come up with a relationship between all these variables. So first of all, this is a right triangle, and we know all the sides. So we know that x squared plus y squared is going to equal r squared. That's our first relationship. The next thing is if we want to include tangent or theta in there, I already spoiled it, we're going to have tangent of theta be y over x. So we can include both the x and y and then this relationship with theta. Oftentimes you'll see it right like this, but you can also see it written as theta is arctan or inverse tan of y over x. So I just take arctan of both sides. Both of these equations are totally valid. All right, so this is usually how we get r and theta from x and y. If we want to go the other way, well, what we can do is we can notice that normally if this radius were 1, then cosine of theta would be this length right here. But since we multiplied this by r, we also multiply the horizontal distance by r. So x will be r cosine of theta, and in the same way, since y is vertical and sine represents vertical distance, y is going to be r sine of theta. So for these 4 equations right here, these are going to be the key from switching back and forth between rectangular and polar coordinates. And we'll get practice doing some of that stuff today. All right, and then one final thing I want to talk about is drawing in polar coordinates. Kind of like drawing the parametric equations, the best way to draw with polar coordinates is to plot points and then see what the general shape looks like. Let's try that out with a relatively simple polar equation here. Why don't we start by drawing r is cosine of theta. Here are my axes. And then I'm going to make a table of theta and r values. And I'm going to keep drawing until I get a general idea of what the shape is going to look like. I'm going to start by plugging in some angles. So why don't we start at 0? That's in this direction. If I plug 0 in for cosine here, I'm going to get cosine of 0 is 1. So in the 0 direction, I go out a distance of 1. Why don't we say that's right here? There's my first point on my curve. I'm going to go by pi over 4. I think that will give me enough detail to see what's going to happen. If I plug pi over 4 into cosine, I end up getting root 2 over 2. The root 2 over 2 is like 0.7-ish. So that's going to be a bit closer to the origin than that first point was. So if it's in the pi over 4 direction, then the distance is a bit shorter than that. Connect these by a curve. And let's go to pi over 2 next. The cosine of pi over 2, that's going to be 0. And remember, whenever our r value is 0, we're automatically at the origin, no matter what our angle is. As we're heading in towards the angle pi over 2, our curve is going to hit the origin. All right, let's keep drawing this stuff. So I have 3 pi over 4. Cosine of 3 pi over 4 is negative root 2 over 2. Now, this, remember, the negative numbers are a bit strange. So normally 3 pi over 4 is actually in this direction, but instead of going this way, we're going to go backwards. And how far are we going to go backwards? Well, this was also root 2 over 2, so we're going to go back that same amount. Okay, there's our next point. And then finally, let's draw pi, see what pi is. Cosine of pi is negative 1, but the pi direction is this way. So rather than going 1 this way, we're still going to go 1 that way. That's actually the point where we started. So we end up back where we started. Now that doesn't necessarily mean that we're done with drawing the curve. Sometimes they'll come back and then we'll go a different direction. But if we start tracing out the same path again, then that means we're done drawing. All right, why don't we go to the next angle, which is 5 pi over 4. Well, cosine of 5 pi over 4 is also negative root 2 over 2. And 5 pi over 4 is this way. So rather than going root 2 over 2 this way, we're instead going to go this way. But then we see we're actually tracing back the same way again. So we don't really even need to go this far, actually. We actually got the whole curve by just looking at this right here. So once we start tracing the same path again and going through it once more, we can stop. All right, now if we take a look at this, what does this look like? Well, it looks like a circle, and it actually is a circle. So this is a circle of diameter, not radius, but diameter 1, and it goes in the positive x direction with its leftmost edge at the origin. So cosine of theta, that's going to be a circle. And if I put like another number in front of this, like 2, then this would have a diameter of 2 instead, but it would still have its end be right there. Now, if I put a 2 inside here, unlike what happened with parametric equations where it was still a circle, put 2 in there, it's actually going to change the curve significantly. So that won't be a circle anymore. And by the way, in the same way that this is a circle, if I were to draw r as sine of theta, and I'll just draw it out real quick without plotting points, then that will be a circle of diameter 1 again, but it's going to be in the positive y direction since sine represents y, or vertical. So we're going to have something in the y direction that will also be a circle. And just like cosine, I could put a coefficient there and make it a bigger or smaller circle. All right, so one final thing I want to draw is something a little bit different. So we could have drawn this in, or we could have represented these in Cartesian coordinates as well. It'd be a little bit more complicated because we have a different center and a radius of 1/2, but it would be possible. Well, let's draw something that would be a bit more difficult to do with rectangular coordinates. Let's say this time my polar equation is going to be 1 minus, let's see, 1 minus cosine of 2 theta. So this time I'm putting the 2 inside the cosine. Let's see what happens with that. I'm going to have my table again, theta and r. I'm going to have my axes right here. All right, and then let's do the same thing we did last time. Let's start plugging in points until we see that it's going to intersect itself, or maybe there'll be some other pattern. That'll let us know we can stop. So I'm going to start with 0. I'm going to put 0 into here. Cosine of 0 is 1, but then 1 minus 1 is 0. So it looks like I actually start at the origin of this one instead of 0. All right, let's go by pi over 4s again. That's usually a pretty solid increment to go by. Unless this number is really high, then you want to go by smaller numbers, like maybe like pi over 6, pi over 8 or something. For pi over 4 right here, if I plug that in, 2 times pi over 4 is pi over 2. Cosine of pi over 2 is 0. So 1 minus 0 is 1. When I'm in the pi over 4 direction, I'm going to go out to 1. Let's say this is 1. Okay. So far, so good. That could still just be a circle again, but who knows what's going to happen. Pi over 2. I plug this into here, and then 2 times pi over 2 is pi. Cosine of pi is negative 1. 1 minus negative 1 will be positive 2. This time, say 1 is right there and 2 is right there. This time I'm going to come up to 2. There. All right, let's keep going. 3 pi over 4, that's going to be cosine of 3 pi over 2, which is 0. So we end up with 1 again because we do 1 minus that. So I'm going to come around this side right here. And then finally, let's take a look at pi. I have cosine of 2 pi, which we know is 1. 1 minus 1 ends up giving us 0. So we end up back here again. You may expect if I went to 5 pi over 4 that I would just trace around the same thing again. I would get this kind of wonky looking circle. But if I do 5 pi over 4 here, let's see. So this is going to be cosine of 5 pi over 2, which is 0. So I end up getting 1 for this. So rather than tracing the same curve again, I actually end up coming out this way here. And it looks like I'm starting to make one of these again. Now here's one trick we can do to save ourselves a lot of time, because my guess is it's probably going to do the same thing again, coming around this way. So here's some information on symmetry. So if r equals f of theta is an even function, and remember what an even function means is that if I stick a negative sign inside everywhere there's a theta, it doesn't really change the function at all. Then there's symmetry about the x-axis, meaning that what I could do is I could take everything that appears up here and I could flip it and have its mirror image down there. Since I have this oval up here, I can also have that down here as well. And then it sort of makes this figure 8 shape. So whatever I have up here will appear over there. It also works the other way too. If I had something down here, it will also appear on the top as well. And that's for even functions. And this is even because if I have r of negative theta, that'll be 1 minus cosine of negative 2 theta. But then remember, cosine is even. So this will be 1 minus cosine of 2 theta, which is just the original function. Now, in the same way, so this one isn't an odd function because it's even. But for odd functions, if r equals f of theta is odd, like maybe I have like r equals sine of theta, for example, that'd be an odd function. Remember, the definition for odd is f of negative theta is negative f of theta. Then there's going to be symmetry about the y-axis. So whatever appears on one side of the y-axis would also appear on the other. So we'd be able to do a mirror image over on this side as well. And it seems like coincidentally this one was also able to do that as well, even though it's not necessarily an odd function. So sometimes you get a coincidence like that. But if you do have an odd function like sine, then it will definitely do. So it'll definitely be symmetric. It'll be symmetric around the vertical axis instead. All right. That's all I have to say for now. But as always, if you have any questions, let me know, and I can help you guys out.